So first, let us look at the introduction of this friction. Maybe you guys all know this friction. In Chinese, we call that 摩擦, you know, 摩擦. So friction is a force that resists the movement of two connecting surfaces that slide relative to one another. Actually, it is the force which will prevent that relevant movement from happening. So this force always acts tangentially to the surface at the points of contact and is directed so as to oppose the possible or existing motion between the surfaces. No? So maybe you look at the picture, it's more easy for you guys to understand. You know, actually, if you guys just neglect all this Chinese character, maybe you guys don't know what it meaning, but it's okay. You can just look at the figure, right? So if we have this device, actually, maybe we do some very simple experiments. So we have a box on this horizontal plane, right? With rope, maybe we have a weight here. So you see, actually from the force analysis, we can easily find when this weight is not big enough, actually it will let this rope to pull this box have the intent to move along this direction, right? On the vertical line, you see it have a support with Fn and gravitational force P. So we have sigma Fy equals 0, so P equal, actually we can use Fn minus P equals 0. So Fn is magnitude will equal to P. So we all have this life experience. If this weight is not big enough, we'll see actually this box will be in a state at here, will not move, right? So it will in a state of equilibrium along horizontal line that is x direction and y direction. So we can give another equilibrium equation that is sigma fx equals 0. So we have ft, which is driven because of the weight of this this thing, right? So actually we have ft minus fs equals 0. So this fs actually is the friction, you know, actually sliding friction. It is the force which prevent it's capable of moving along positive direction of x from happening. Do you know? So actually we can find, because of the equilibrium equation, this friction is magnitude Fs will equal Ft, and its direction will opposite Ft because it will prevent this capable of moving along this direction from happening, right? But there is a very famous scientist who found the so-called Coulomb friction law, you know, Coulomb 摩擦定律. So when we let this weight bigger and bigger a little bit one time, maybe in some time, you guys can understand that, we call that a crystal point. That weight will be big enough that this box cannot keep its balanced state along x direction. Then we know that the biggest fraction of this force can be, we can find that. Actually, at that critical condition, it will move and not move. At that critical point, we have this equation, you know, F max equal Fs times Mn, which Fn is support force of this. So this is so-called friction law from famous scientist Coulomb, right? So that is friction. So we can look at this slide. Actually, it has English version. So we can talk about category of friction. It can be divided into different category from different point of view. So actually, it can be divided into sliding friction and rolling friction. So if the two bodies, their relevant, their relative moment will be translational moment. So we call that sliding friction. Because of this sliding friction force prevent this capable of relevant movement along some line or some direction from happening. So we have static sliding friction. So if it is static sliding friction, actually these two bodies have no relative moment, right? We also have another dynamic sliding friction. This case, because it exceeds relative moment from one body to another, which keep in contacting in some surface. We also have a rolling friction. If the relative moment will be a rotation from one to each other to another, then it also have static rolling friction. Actually, it has the intent to roll, but it's not rotation, right? And dynamic rolling friction actually always have relative rotation movement. We also have another divided characteristic, which is dry friction and wet friction. So actually, this is very difficult science branches. So we have a terminology called that tribology maybe. We Chinese call that 摩擦学. So we only need to have some basic concept about friction is enough. Then we'll move to the second part of this course. Okay, so maybe I will not read all the sentence of the first section introduction. It tells us what is friction. See, so actually we can find there is a tire, maybe there our shoe. Actually, it is friction. Help us can drive a car, can move on the road, right? So let's see, friction forces are present throughout nature and exist in all machines, no matter how accurately constructed or carefully lubricated. Actually, this lubricated means, I don't know how to express this. Actually, in China, we call that 润滑. Maybe it lines the two surfaces of two bodies will contact one to each other. We have some fluid thing to make the friction between one body to another to little as possible as it can be. So this is some kind of lubricated, you know? So friction appears at physical interface between two surfaces in contact, and it occurs in all mechanical systems. Actually, it occurs in all mechanical systems, but all the things, all the problem we have learned, we have tackled before today, we neglect all the frictions, you know? So in engineering, some devices are driven by friction. Example, bearings, transmissions, hydraulic and pneumatic cylinders, brakes, and wheels, right? However, friction will introduce unexpected vibration, distortion, abrasion, etc. So it not means friction is a bad thing. We should totally eradicate it as possible as we can. Actually, it depends. You know, in some cases, friction is very helpful to fulfill some mankind requirement, right? So let's see. Actually, friction is handy there sometimes, you know, not all the time, it's sometimes. And engineers do everything possible to reduce friction. So in some types of machines and processes, we want to minimize the retarding effect of friction forces. So in my opinion here, the retarding effect may be in the negative effect of the friction force, right? And a machine adopts lubricating oil, 润滑油, to reduce friction. Contrarily, in other situations, we wish to maximize the effects of friction, right? Actually, in these situations, we are using the friction. It helps us to fulfill some mankind's requirements, such as brakes, brakes and clutches actually is another kind of brakes, backdrafts and wedges, and some machines run by the mechanism of friction. For example, wheeled vehicle, maybe car, maybe bus, right? And sand brakes depend on friction for both starting and stopping, right? So that's what the friction all about, because it's very difficult. So I only need you guys follow me, follow my introduction of this. We have a basic concept of friction. That's enough, right? So we'll move to the second section, talk about the types of friction. Actually, it's not very, it's not very important. Actually, we have discussed this friction. We can this and this. So let's see. In general, friction is the force resisting the relative motion of solid surfaces, right? And fluid layers and the material elements sliding against each other. There are several types of friction. We should know a little bit, right? So the first one, the dry friction. Dry friction resists relative lateral motion of two solid surfaces in contact. It occurs when the unlubricated surfaces of two solids are in contact under a condition of sliding or tendency to slide. Actually, it's not slide, but it has the big tendency to slide, more like the figure of this, because of the weight of this box, so it has the tendency to move along the positive direction of x, right? So a friction force tangential to the surface of contact occur, both supporting the interval leading to impending slippage and while slippage takes place. So you guys please pay attention to the underlined sentence. The direction of this friction force always opposes the motion or impending motion. So we can look this figure again. Because of this driven force Ft, it's more like to let this box to have a movement relative to this fixed ground along positive direction of x, right? But we will have a friction Fs, which direction is opposed to this direction Ft. This force prevents this tendency from happening. So if Ft is not that big enough, right? So if we keep increasing the value of this Ft, so in some crystal point, we will have this F max, although we can give some friction, but its biggest magnitude is limited. It equals Fs times Fn. Actually, this is coefficient. It will give according to the material of this box and this ground, So this is Coulomb law of friction. So back to the sentence, I only need you guys have some basic concept of this. That is what dry friction are about, right? About. This type of friction also called Coulomb friction, Coulomb friction. The principle of dry or Coulomb friction were developed largely from the experiments of Coulomb in 1781, long time ago. So this is a very famous scientist who found this law of Coulomb friction. So we call that Coulomb friction. No? So the second character is the fluid friction. So fluid friction occurs when adjacent layer in a fluid, liquid or gas are moving at different velocities. So you can compare from this fluid friction to this dry friction. If the two bodies are in dry friction conditions, actually it should in the state of balanced. But when we talk about fluid friction, actually, it tells us moving at different velocities, right? These two bodies have a relative movement along the tangential line, right? So this motion causes frictional forces between fluid elements. So this kind of friction we must have the fluid to lubricate these two friction surface. Otherwise, the machine will be very badly damaged. And these forces depend on the relative velocity between layers. When there's no relative velocity, there's no fluid friction. A fluid friction depends not only on the velocity gradients. Actually, this may be it's a mathematical terminology within the fluid, but also on the viscosity of fluid. So anyway, you just know that a kind of fluid friction. We will not talk about some deep concept of this. We also talk about another friction. It's called internal friction in materials, right? So internal friction occurs in all solid materials which are subjected to cyclical loading, 周期性载荷. For highly elastic material, actually it is not because we have a assumption of rigid body, but here we are talking about highly elastic material recovery from deformation. So for highly elastic material, recovery from deformation occurs with very little losses of energy due to the internal friction, So that is the internal friction. For materials which have low limits of elasticity and which undergo appreciable plastic deformation during loading, a considerable amount of internal friction may accompany this deformation. Because when we talk about elasticity, it was if this material have some deformation under some kind of loading, when the loading is removed because deformation is elastical. So all the deformation will from some value restore to zero. So all this process maybe have some energy, you see, amount of internal friction. So because of this kind of internal friction, so maybe have some energy consumption. So this can mean internal friction in material. The mechanism of internal friction is associated with the action of shear deformation. Actually, this is 剪切变形，剪。No? So actually deformation means 变形, shear means 剪切. So maybe you have a sheep, you will have a big scissor to cut the long fur of your sheep. So that means scissors. In China, we call that 剪. So you can think about when you maybe share the fur of the sheep with the big scissors. So you can think about the direction of the shear force into the fur of the sheep. So we call that shear deformation. Actually, discussed in material science, actually in we will talk about next semester. We call that 材料力学 you know, 或者工程力学2。So this semester we are learning engineering mechanics 1. Actually, material science will be engineering mechanics 2nd, right? So anyway, you guys only need to have some basic concept is enough. So we'll move. We also have sliding friction and rolling friction. So because of time, I will not read all the sentence for you guys. So maybe you guys can take your time after this class and read this whole chapter by yourself. Okay, so let's move to the section third, talk about the theory of sliding friction. Actually, it has a lot of sentence here. If I read all this, it will take our lot of time and very boring. But we can just look at the picture to tell you guys how to find its sliding friction. So you can see this picture. Imagine that we have a horizontal plane and we have a box. You know, so this is the active force maybe acting by us onto this object. So you can see actually this force, it has a tendency, you know, to let this box to move along the positive direction of x, right? But we also can understand that because our life experience, if the box is big enough and if this FP is its value is very limited, we will find although we have this direction of FP, but this box will in the state of balanced. In other words, it will be in the state of stationary. So if this box is in state of stationary, we call that it in the equilibrium condition. So we can do its force analysis and give the equilibrium equations, right? So actually from the type of constraint we have learned, actually we know that we have a support reaction Fn here. We have active gravitational force because of its mass, because of the Earth. So it has gravitational force G here along this center of mass, right? It's very easy to understand. So why this box cannot move along X direction when this box is big enough and this FP maybe is little enough, right? So there should be have a what? Have a Fs, right? We can use that Fs. Here, the subscript S means it is what? A sliding friction, right? We call that a sliding friction, 滑动摩擦. So, since it in the state of equilibrium, we can use what we have learned equilibrium condition. So we have sigma fx equals 0. So fp matches, I think this ff use fs is more helpful for us to understand, right? Anyway, we know that actually this sliding friction will equal fp, right? And because along the y direction also in the state of balance, so we also have sigma fy equals 0. So Fn minus G equals 0, right? That's the whole process of analysis. So we can call that experiment. So the experiment involves application of horizontal force Fp, which continuously increase from 0 to a value sufficient to move the block and give it an appreciable velocity. You know, actually, it's more like the figure we have discussed before, right? It's more like this. So let's say as explanation, if the force Fp exceeds a certain limit, so that means we have a critical limit. The box will sleep on the base, right? So correspondingly, we call that F max is the maximum of the friction force these two material contact one to each other can provide. So F max means the maximum value of FF, which FF is the friction, is the sliding friction. Can you guys understand that? So this is F max. So we call that limiting static friction force. When Fp equal F max, actually this is the so-called critical point. The box is in the unstable equilibrium. It is the critical state, Actually, I just use this critical state. In Chinese, we call that, I can show you guys, in Chinese, we call that 临界条件，临界状态, So this critical means 临界. That means something will happen, but not happen. Can you understand? So that is the critical state. Because before this critical point, it's always in the state of equilibrium, because we always have Fp equal Ff. The bigger Fp, the bigger this Ff will be. But its maximum value is limited. It cannot increase all the time. So at some critical state, if you still increase your Fp, Ff cannot increase anymore, right? Then it is a critical state. So as shown in figure 5 to C, that means after this critical point, because F max reach its maximum value, so it cannot balance or offset this Fp again. So this box will move along the positive direction of X. See? Actually, that's the theory of sliding friction. It can be seen that the direction of the friction force is always opposite to the tendency of motion. So we'll talk about this Coulomb theory of friction. So please pay attention to here. This is a very important point. I hope you guys will know that. So let us first consider static friction using example in this figure. Right, in this figure. And as long as Fp is smaller than a certain limit F max, so actually we have this, we have this condition. Can you look at this? We have this condition. So that means as long as Fp is smaller than a certain limit F max, the box will always stay at rest and equilibrium, and this condition is applied. Fp equal Ff. So you guys can think about that. Actually, Fp is active force, and this Fs is another kind of reactions, right? If you bigger a little bit, I will bigger a little bit, always keep the state of equilibrium, right? So the tangential force F attained its maximum value. And the normal force is defined as the net force compressing two parallel surfaces together. And its direction is perpendicular to the surface. In the simple case of a mass resting on the horizontal surface, the only component of the normal force is the force due to gravity, However, the coefficient of friction is not a function of mass or volume. You know, this is important. It depends only on the material. That experiment is tested by Coulomb, maybe. So, for instance, a large aluminum block, you know, this is a kind of famous material. It will be used very often in engineering. You know, in China, we call that 铝. Do you guys understand this? 铝. Maybe I can show you this character. 旅行台. Sorry. So when you say a Chinese character with this left part, it means it's a kind of metal, you know? So we call that 金字旁, right? Because of this, maybe I can show you guys another material. Do you know 铁? No? 铜. So maybe this is copper, you know, you guess actually this three character means three different kind of metal, which is always used in engineering. We also have another steel. Do you guys know steel? We Chinese call that 钢材. No? 钢材. It's very often used in engineering. So there are a lot of metal material, right? So actually, it just show tell us F max equal Fs times Fn. This is support reaction because of along the normal line direction, which is perpendicular to the direction of Fs, you know? But this Fs, actually it is the coefficient. It only because of the type of material, you know, the type of material. So this is so-called theory of sliding force, sliding friction force. So the proportionality force factor Fs is commonly referred to as the coefficient of static friction. We Chinese call that 静摩擦系数. Static means 静, not move. 摩擦 friction, coefficient 系数. No, it's 静摩擦系数 Fs. It depends solely on, so please, you guys, you must know that. This Fs, it depends solely on the roughness of surface in the contact, irrespective of their size. So maybe I will open my video. So hope you guys can see. So we can hold our two hands, you know, let our palm to contact one to another. So when you move and when you push very hardly and move it again, maybe just several times you will find very hot, right? Do not do that often. If you keep doing this, you can find you will hurt yourself, right? Because the heart is like the temperature rise big enough, then maybe it will hurt your skin. This is because of friction, you know? So our two hands together is Fn, right? This Fs is according to roughness of our palm, right? So actually this is friction. Do not do that. So when the temperature is low, when you feel very cold, you don't have gloves, you know, so you can move, you can let your hand to have some feelings, right? So a body adhere to its base as long as the condition of static friction is fulfilled. you know. So there are very important things, please, you guys, you must know. We have this condition, FF, it will greater than 0 and less than or equal F max. Right? But we can never use this equation to calculate FF. No? So if we make sure that this box is in the condition of critical state, in other words, only the maximum of this static friction fulfills this equation, right? We never use this equation to calculate FF. Actually, if it is FF, it will, in the state of equilibrium, we always use this equilibrium condition to find the real or actually value of FF. Never use Fs times Fn. Only in the critical state or only when we try to calculate F max, we use this equation. That is very important, okay? So we also have to talk about another important things maybe you guys should know. The normal force Fn, right? Actually, it is a kind of reaction, right? Because this fixed ground supports this box, maybe, right? So if their tendency let this box move along this direction, so we will have a sliding friction effect, which will prevent this tendency from happening, right? So actually we can think about that FF is another kind of reaction force. Its value we will according to the driven force, right? So, so since Fn is a kind of reaction force, FF is another kind of reaction force. So we can do things. Because this Fn it can along from its action line. So we can let this Fn and this Ff have the same or common point here. So from the parallel theorem, how we use that to find the reluctant force of two forces. We just need to draw a parallel slide. Actually, this is rectangular. So we get this Fr. Actually, Fr equal this Fn. It's very hard to write something on this screen. Plus, FF. Hope you guys can understand me. So we just use this theorem. We will find this reluctant force Fr, and we give a name to it, total reactive force. In Chinese, we will call that 全反力. So you see, actually Fs, its value will be 0 to F max. And here is Fn. So you can see its direction is defined by the angle phi. So which can derive from what? So actually we have this. We have this tangent phi will equal here is FF. I think I think this is not, because this is FF, so this expression is not correct. It should be what? It should be FF, so maybe I write it here. So this is an error of this textbook. Please, you guys should correct it. So tangent phi should equal FF. Over Fn. So suppose that Fn will always equal gravitational force of this box. So its direction and magnitude will keep the same. So we can say actually Fs will from 0 to F max. So you will see if Ff equals 0, then tangent phi will equal 0. So this direction of Fr will have intersect angle phi equals 0, right? And when Ff, when Ff reached to its maximum value, F max, you see? Which one from the law of Coulomb friction law, we know that actually this one equal coefficient Fs times Fn. Right? So we can substitute this expression to here, and then we can find this maximum value of phi. So we call that tangent phi f will equal what? It's very interesting, because Fs times Fn over Fn is only equal Fs. So actually we call that this angle phi f called that angle of friction. In Chinese, we call that 摩擦角. No, we call that 摩擦角, angle of friction. 摩擦角. No, we call that angle of friction 摩擦角. So you can see actually different material, it will have different coefficient of Fs. So its value of 摩擦角 phi f will different, right? So this is a very interesting knowledge point. You see? So here we can talk about this. So let's see, contact material, maybe metal on S. Can you see that? Metal on S. So its Fs, static friction Fs, may be 003 to 005. Actually, it is a scope, a range from the little one to the a little bigger one, right? And wood on wood here, leather on food, leather on metal, and copper on copper, 铜和铜, right? So maybe we can test our hand to hand, right? Hand on hand, what's the coefficient of that static friction in? Maybe there will have some value, right? Maybe different person will have different value of this. Anyway, we should know that only F max equal Fs times Fn, and we have this angle of friction. So it's noted that the tangential force and normal force only in the limited case when slipping is impending. Actually, it's another phrase tell us it in the state of critical state, right? It will happen, but not happen, maybe I cannot express that in English very clearly, but I hope guys you can understand. It is in the critical point. It will happening, but not happen yet, right? It is not an equation for the static friction force F max. Even though static and kinetic friction are caused by roughness of the surface, their specific nature is fundamentally different. So actually, we also have another 动摩擦 kinetic friction. Actually, we have this FD equal FE times Fn. It's more like the expression of we talk about the biggest value of static sliding friction. But actually, this FD may be a little bit smaller than Fs, and it have fundamentally different from these two kind of friction, right? So after we have this maybe it tell us angle of friction. Actually, this is angle of static friction also means 摩擦角, right? 摩擦角. Actually, I have finished the introduction of this angle of static friction, So maybe I can repeat that, which can help you guys understand more, maybe, right? The angle phi F, that maximum total reactive force FRM makes with Fn, is called angle of static friction. So actually at this time, if we keep Fn with the same direction and magnitude, so our Fmax will equal Fs times Fn. So we have this, right? Actually, I have mentioned this before. So the so-called angle of static friction phi F is only related to the coefficient of static friction because we have this. Actually, maybe I can write like, so means if we know Fs, we can find phi F. In other words, if we know phi F, we can find actually Fs equal tangent 反函数, right? Tangent minus 1 phi F. Another expression maybe ATAN. So we have this kind of function in MATLAB, no? ATAN phi F. We can transform this angle to a value, right? So after we have this so-called angle of static friction, we'll talk about friction cone and self-locking. This is a very important concept. I hope you guys can understand through my introduction. We call that 自锁. So maybe we should have a short break. We will restart our class today at 11:10. So please, you guys have a rest, right?
Okay.
Okay. Okay. I'll mute my voice a little bit. In China, we call that 摩擦锥. That cone, we call that 锥. We have maybe like this shape, right? It's not a cylinder, but it's a cone, more like ice cream, right? And self-locking. So maybe this a little bit difficult to understand. So maybe I'd better read the sentence and learn to with your guys together. So the orientation of the friction force FF always opposes the direction of the motion that would occur in the absence of friction, right? For complex systems, this orientation is often not easily identifiable. Yes, just take X direction as an example. So actually, this orientation may be point to right, also maybe point to left, because it always opposes the tendency of the relative movement. But maybe in some case, we cannot sure what's the direction of the tendency, right? So in that case, we have to assume some direction. Then the algebraic sign of the result shows if the assumption was correct. So maybe you, through your false analysis, and you oppose or assume that FF will along some direction. And then if you find your FF have a positive value, that means your assumption is correct. If you find actually this FF's value is minus, so it shows that actually its direction is opposed to your assumption. right? But we should know that. Can you understand me? If we find, let's say, if we find from the equilibrium condition, maybe FF equals some given value like 500 kilonewton. Is that always true? That means this FF should be equal 500 kilonewtons. No, no, there is another condition we should remember and always test it if it is true. That is our FF must less than or equal to F max. No? So maybe the value of your FF is that you assume that this system is in the condition of equilibrium. And from the equilibrium condition, equilibrium equation, you calculated this FF ought. But if you find this value actually greater than F max, then it means your assumption is not correct. This system is not in the state of balanced. You should not use this to calculate its FF because it has relevant moment already. You know, actually, this is the condition we should test it if or no that assumption is right. So I only need you guys have a impression. I do not require that you know this exactly, right? So I will continue to introduce the so-called friction cone and self-locking. So in we know that actually in different directions we always have FF less than or equal to F max, which equals this Fs times Fn, right? And it tells us in three-dimensional space, the static friction angle phi can also be interpreted graphically. So maybe I can just use this figure to show you guys what is so-called self-locking. You know, it's too hard to read the whole sentence. You know, actually we have the concept, the what is FR, how we call that FR. You know, do you still remember? We call that the total reactive force, FR. Actually, it is reluctant force of Fn and Ff. You know? So from this, actually from this, I can find. So we have Fn and F max. That means this is the friction angle, right? That means if we talk about the intersect angle between Fr and Fn, phi f is the biggest angle it can be, right? It can be. So that means you guys please pay attention to my currently explanation. So if we have active force Fp, you know, so actually we have this Fn, F max, and Fr. So we have this triangle. So if you guys know how to make a three-dimensional figure, use different software, maybe SolidWorks or ProE. Do you guys know this software, SolidWorks, you know, or UG, or ProE, UG. These famous software will help us how to build a graphical things with 3 dimensions. Actually, we can just use this triangle, let it rotate around this vertical line. Actually, we call that sweep precise, sweep or sweeping. So actually, we can get this cone. We call that friction cone. Why? Why? Can you guys understand? Actually, this direction of friction actually is because of the active force. So if you look from the how to say, from this direction, look at this plane. Maybe I can draw your view like this. So maybe you can look at this ground plane. There is the box rest on this plane, right? So maybe I will change the color. So if we have a positive force along this direction, right? It will try to let this box move along this direction. Then we'll have opposite direction of friction to prevent this tendency from happening. We also have, if we have another active force acting on this box, try to let this box move along this direction. Then we also have another friction force to prevent this tendency from happening. Actually means this friction force can along different direction totally according to the active force. You see? So actually at different direction, we always can give this similar triangle. So we can let it do a sweeping precise, then we can get this cone. We call that static friction cone. Can you guys understand this? Can you? Actually, because of different active force, so our direction of friction force also along different direction actually have 306 degree, right? So we will have this friction cone. So that means if we have a positive force or active force, its action line is in the cone, then we only need our FR have the same magnitude, opposite direction, and collinear with FP. Then these two force, this is the total reactive force FR, and this FP will offset one to each other. So it will be in the state of balance. So maybe this time we have an intersect angle. We call that phi1. So next time, maybe you have another active force. It's still an internal because it's intersect angle with the normal line, always less than phi f. So it's always in this cone, right? So we will have alpha like this. So it calls that if you can keep this active force always its action line always internal this static friction cone. No matter how big the FP is, it will always in the equilibrium condition. This is so-called self-locking. It's called self-locking because how big this FP will be, we always will have FR have opposite direction, same magnitude, and collinear with this, right? So no matter how big this FP is, it will always keep the equilibrium condition. So we call that self-locking. And if it's in this station, so this time you guys look at this picture. If we have another FP, but it intersect angle between its action line and normal line, its phi is greater than phi f. So our FR, if we try to offset this FP, it must have same magnitude with FP collinear with FP and opposite direction with FP. But its maximum angle between FR and this normal line is phi F. You know, it also reach its maximum phi F. It cannot move along this direction anymore. Can you guys understand? So it cannot be like this, right? Just the opposite direction of this SP. So if this applies, then our intersect angle will be this. But it will not true because we require this phi will always less than or equal to phi F. This will not apply. So actually, it's not reality. That means you are maximum angle of friction is phi F. So this is the limited direction FR can be. It cannot rotate along this direction, try to offset this FP. So if this is the case, then we have the conclusion. At this state, no matter how small the FP is, this box cannot keep the state of equilibrium. Can you guys understanding? No matter how smaller the FP is, because its action line, its direction. So we don't have FR, which can offset it because of the angle. So this time, no matter how smaller the LP is, this guy have to be moved. It cannot rest anymore. So that is, so back to this. If this FP is always internal this cone, it can be any direction as long as its direction in its intersect angle with Fn or normal line is less than phi F. It can be any direction. As long as it's internal this cone, then it will always in the state of equilibrium. Can you guys understand that? We call this self-locking. That means self-locking, you know, self-locking, 自锁. So this means no matter how bigger this FP is, this equilibrium state cannot be changed. Always keep the condition of equilibrium. So that means, so actually this so-called self-locking is very important in some engineering case. Let's say a screw jack is a typical application of self-locking. It can lift and hold up heavy weight without any braking mechanism. So you guys can see this. Maybe do you guys familiar with device? So if you have a car, maybe sometimes you are very unlucky. There's some problem with your car. It cannot move anymore, right? Maybe our tail just be punctured by some nails or something. It cannot move anymore. Then we can use this. Actually, in Chinese, we call that, actually, we have very famous name called that 千斤顶. No, we call that 千斤顶. That means you can rotate this screw device. Then this guy will move along the upward direction. It will lift your car. Maybe then you can unload your tire and fix it. Then you can you can fix your tire. Then how to say? Can you guys understand what I'm trying to tell you guys?
Yes, Lausi.
Yes, that means although the weight of this car or this something is very big, but it cannot let this part to rotate around the opposite direction. So this one will move downward. So that means it will very safe, it's very safe. So you guys, please, you should know that our talking about self-locking have direction. It have the direction condition because we only the only condition is no matter how big this FP is, but its direction must within the friction code, right? So this is the typical use. So it can lift very big things without that thing will move along the opposite direction itself. So very safe, right? So that is the safe meaning. Actually, we have elevator, we have something, because when we design some transmission device to lift some very heavy things, we always hope that it's in the self-locking condition. Then it will prevent some unhappy efficient happening, right? Events happening. So that's the very important concept, self-locking. I hope you guys can understand, can have impression. And I think for the friction, I also have another concept. I hope you guys can understand. So actually, we also have another two pictures. So one is the blocks is self-locking, and this gas screw is non-self-locking. Actually, it tells how to use so-called self-locking, right? So another things maybe I think so this section will skipped. So equilibrium problem of the body with friction, because this topic is too difficult for you guys. So if you are very interested in this topic, so you can look this content by yourself. If you have some question, you can discuss with me. And we will not touch this topic together today. So there are a little things about this friction chapter I want you guys to know in another rolling resistance. So I only hope you guys can have some basic concept. So actually we call that in Chinese 滚动模组. So actually, we just finished discuss friction, sliding friction. Actually, this so-called rolling resistance, it means it can resist that rotation from happening. So I think we all have life experience. So if there is a very big ball, maybe it's very heavy, it's made from metal, maybe. If it is big enough, if we just use our hand to push, let it run on the ground. So it may take our big endeavor to let that ball to run on the ground, right? In other words, if your push force is not big enough, it will always rest on the ground without rolling, right? So there is a kind of same concept of the sliding friction. So let's see, let's look at this paragraph. It tells us, it is well known that it is easier to roll a roller than to slip it. That's a very important life experience of our mankind, right? So we know how to move a very heavy things, just let some rollers between under its bottom. Then it's quite easy to move that very heavy things to move, right? So we all know that it is easier to roll a roller than to slip it, right? Actually, however, no materials are perfectly rigid. and therefore the reaction of surface on the cylinder consists of distribution of normal pressure. For example, imagine the cylinder is made of very hard material and the surface on which it rolls to be relatively soft. Looking at the force diagram below, so you guys can look this picture together. So we may bring up a question. Although the body is in equilibrium, it does not satisfy the equilibrium equation completely as shown. So let's say we have maybe a big cylinder here, rest on the ground. So along the vertical line, we know we have support force Fn and gravitational force of this ball. So these two gases will keep in the balanced condition. So that means W equal Fn. But maybe we have asserted a value of force P along a positive direction of X. But this ball or this cylinder do not rolling around do not move, always keep in the rest state. Then we know it should have a sliding force like this, because its tendency is let this ball move relative to this fixed ground. So we have a FF, right? So it's in the state of balance. Since it's in the state of balance, so we can give the equilibrium condition, but we found some problem occur. See? So we have sigma fx equals 0, then P minus FF, right? This is sliding friction equals 0, which is true. So we have sigma Fy equals 0. So we have W, actually we should Fn minus W equals 0. Actually, our correct equation should be Fn minus W equals 0. So you can say actually this equation is the same of this if we time -1 both sides of this equation, right? But the third one, if we use this point A to be a what moment equation, so we have sigma ma equals 0. So you see Fn, Ff, and W, all these three forces through its point. So these three guys have no moment to point A. So we have P times R equals 0. Then if this equation satisfies, then P should be 0, which is controversial to this one. So this P equal FF will greater than 0. Actually, P is the force asserted by us, right? It's true, it's greater than 0. It has some value. So that means it's not correct. So why? The reason is what? Actually, the reason is it also has some kind of rolling resistance, So actually, you can say this P and this F have a moment couple and constitute a couple along the CW direction, right? Actually, it have another rolling resistance. We call that MR, right? Or MF. So it's more like a sliding friction. This rolling resistance is kind of moment which will offset this CW direction couple constituted by P and FF. No, that's why it will have rolling resistance. So it tells us it should have. The reason is because we don't have, actually we don't have 100% rigid body. So if this ground is a little bit soft, so it will push here together a little bit. Although it will very tiny, but it will have a little deformation. Then this will constitute a plane generalized force system. So, when we select a point to simplify a plane force system, we will have a principal vector Fr, right? And a principal moment Mr, right? So that's why this ball cannot run rotation in the state of equilibrium, actually because this Mr. So actually, when we understand why this is happening, so we have this. Actually, because this Fr not zero, this not zero, so we can move a little bit. So we have this. Then we will have this Mr. So this rolling assistance, I'm sorry, this rolling resistance, not assistance, resistance. This rolling resistance more like the sliding force. So we have static sliding frictions. Fx should less than or equal F max, right? And greater or equal than 0. So for the same pattern or same meaning, we also have, there is a range of this roller resistance, M greater than 0, less than M max. And we also have this equation. It's more like we have F max. No, we have F max equal Fs. Right? And so if you guys can understand this, maybe you can understand that. And they are a little different from this one to this one, because this rolling resistance is a kind of moment, right? And this is a force. So actually, this Fs will have no units. It's just a number. But this delta, it will have a length unit, because a moment will be maybe newtons or kilonewtons times a length unit, maybe meters or millimeters or centimeters. So this delta will have a length unit. Actually, this one is very, very small. Delta usually is very small. The first couple of resistance is neglected in most engineering problems. Hence, the rolling friction is neglected, especially when the shape not a cylinder, not a ball, it's a box like this, right? So in this case, the so-called rolling resistance always be neglected. But anyway, you guys should know this concept, especially when the body shape is cylindrical, or box, right? I'm sorry, not a box, or sphere, a 球, right? We should know there have a kind of rolling resistance. So I think that's all for this final chapter, friction. That's all the things I hope you guys can know a little bit. So we don't have homework for this chapter. We still have maybe 20 minutes. Then we'll move to the new part of the medium part, right? That's all for the friction. If you guys are very interested in this chapter, maybe you can read the things we do not cover this time, right? So we still have 20 minutes. We will move into the second part of this course. So actually we will move to this. So we will talk about the second part of kinematics. Kinematics. Am I right in reading this? Actually, in Chinese, we call that 运动学. Actually, we just finished studying statics, STATICS. we call that 静力学. No, actually, this part we talk about how system its equilibrium condition is, right? We just know how to give the correct force analysis and through the three famous equilibrium condition to find some unknowns, right? And this the second part of this whole course, we call that 运动学 in English. It's not very familiar for me. It's called kinematics. Kinematics. This is the second part of this course, and this is the first part. And the final third part of this course is 动力学, you know, 动力学. 动力学 dynamics, how to say, dynamics. So maybe you guys think about that statics is a little bit difficult for me, some problem I cannot tackle by myself. Actually, it's just the beginning, you know, you guys will find actually kinematics also another difficult topic for you to understand. Anyway, I will try my best to do the best explanation to you guys, and maybe we'll do some typical examples together to help you guys have a deep understanding of this part. After we finish this part, we will move into the final part of this course. That means dynamics. Actually, it's because of second law of Newton's. Do you guys still know the second law of Newton's? F equal ma, right? So actually this second part, we talk about displacement, velocity, and acceleration, right? And the statics, we talk about sigma f equals 0, it's in the state of equilibrium. But if this system is not in state of equilibrium, then it is the force to let it move in some pattern, in some maybe move along some line, will rotation around some lines. So we will use this second law of Newton's to link force and coefficients of kinematics, right? Actually, that's why we have to learn kinematics. So prepare all you guys. Maybe if you have time, you can read the content of the textbook accordingly. So since we only have 15 minutes, we will do a brief introduction of this second part. So let us look at the basic concepts of kinematics. So what is kinematics? What is kinematics? I try to find my pointer and write something on here. So okay. So what is kinematics? The science of the relation between a given motion of an object and time. You know, it is a science that research or study the relation between a given motion of an object and the time, right? In which only the geometrical characteristics of the motion, such as trajectories, velocities, maybe trajectories, maybe paths. In Chinese, we call that 轨迹, 轨迹, right? And accelerations are studied, but not the reasons for the motion considered. It means we only focus on how to find the relationship between trajectories, velocities, and accelerations. But we do not think about the reason why it has this kind of motion, right? And objects of kinematics, 我们的运动学的研究对象. The first one develops the method for describing mechanical motion. Actually, you guys will find we will start from starting the movement of a point. We call 点, right? Actually, we can find a lot of points will constitute a rigid body, right? We call that 钢体. And then we'll talk about 物体系统. So you guys will find actually we will along this road to introduce the whole concept of kinematic to you guys. So the first 点 means point, right? Point. And then 钢体 means a rigid body because according our rigid body assumption, it under any loading, it will have no any deformation, right? So any 2 points on the body, it will have no relevant movement. So if we have information of 1 point on the rigid body, maybe we will have the power to find any other point on the body because it's in the same body. So the different point maybe have some relationship between their movements, right? We have a lot of bodies, and then we have some common type of constraint which we can constitute a body system, right? Body system. Then we'll talk about the movement of a whole body system. That's the logic load of this whole part, right? So we'll talk about develop describing mechanical motion from point, right? And establishes the relations between the variables related to motion. Why should we start it? Because it is the foundations for the following courses and direct application in engineering practice. So maybe next semester, you guys will have to learn another engineering mechanic too. Maybe also by me, by Fang Ruiming, right? Actually, you guys also have to learn another course. Maybe its name should be Principle of Machinery. Principle of Machinery. In Chinese, we call that 机械原 of our mechanical engineering student, right? That course is very important. And it will talk about the movement of body system. So at that time, you guys will have to use the knowledge we have learned at this part. That's why we started. So because of these two main reasons, we have to start it. And the classification of motions. So the motion of particles. Particle means 粒子, right? Or 质点. Actually, it is a 点, right? It is a point. So we first start to study a motion of a point. Then we move to study motion of a rigid body. Why? Because a rigid body is constituted by a lot of points, right? It's constituted by a lot of points. If we know 1 point is motion, then maybe we can know the other point of this body. So you can see, so this path is very logical. Maybe it's easier for us to understanding things from simple to complicated ones, right? So let's continue. We will start from chapter 6, kinematics of a particle. In Chinese, we can call that 点的运动, right? 或者点的运动学 kinematics of a particle, 点的运动. So you guys can just look at particle at a very tiny point on some rigid body. So there will be third sections in this chapter. We'll talk about description of the motion of a particle using a vector of position. So we should very familiar. We talk about force, is a vector. We talk about moment, it's a vector, right? So a vector have three factors. The magnitude we call that 大小. Another direction we call that 方向. And what's the third one? The main is 大小 方向. Of course, we also have application line 作用点作用线. For a moment, we have applied plane, right? So it has some familiar concept of a vector. You guys will see when we move to that part. Today we don't have enough time. Maybe we just have very short introduction of that. The second will be description of the motion of a particle using rectangular coordinates. Actually, the first description will give us maybe a vector direction, right? A vector direction. It can help us to familiar when we try to study the movement of a point named M. So we just study the vector of OM. It will change its magnitude and direction at different time moments. So we have function vector RT, but it cannot be used. So we will have to projection on this vector into three axes. So we have the second direction, which means description of the motion of particle using rectangular coordinates. We call that 直角坐标系. So we have maybe X, Y, and Z. So at first, you guys will find, wow, it's very complicated. But the good news is, when we finish this description, we will find in many, many cases, we will always focus plane in motion. We will plane in motion, just more like the first part, we always focus on plane in generalized force system. When we just study the plane motion, it will only have two axes, X and Y, right? The third section will be description of motion of a particle using natural coordinates. Maybe this one will let you guys find a little bit difficult to understand, but we'll try. That it will tell us if we know the path or trajectory of a moving point. So before we started its motion, we already know its path or trajectory along this. Then we can use this so-called natural coordinates to describe its motion, right? That's all for this kinematic of particle. It's very important. It's a basic knowledge of when we start to study the kinematic of body, or rigid body, then to the body system, right? Actually, we should start the first section, but we only have 3 minutes left. So I think we better stop here, right? So I think we should stop here. That's all for today. And today we don't have homework for you guys, but I hope you guys can read this part before the next class. We will learn this together, right? So that's all for today. Bye bye, you guys. 今天就到这里吧，好吗？今天下课吧。
OK，老师，
OK，拜拜。
拜拜。